Welcome. There's a moment in every C++ developer's journey where they realize they've been doing something the hard way. For many, error handling is that moment. Many codebases still jump straight from raw return codes to exceptions, missing the expressive types that modern C++ provides. In this lesson, you'll learn 3 standard library types that model absence, alternatives, and recoverable failures. By the end, you'll choose the right error model for each situation, and your APIs will be clearer for it. Let's get started. Modern C++ gives you 3 tools for error handling beyond exceptions and return codes. First, std optional of t for maybe a value. Use it when absence is a normal outcome and there's no need to explain why. Second, std variant of multiple types for one of several valid alternatives. Use it when the result could be any of a fixed set of types, all of which are valid domain states. Third, std expected of t, e for either a value or a typed error. Use it when the caller needs to know what went wrong, not just that something failed. Choosing the right model makes your APIs easier to read, easier to test, and harder to misuse. Optional is the simplest of the 3. It represents a value that might or might not be present. In this example, find port takes a service name and returns an optional int. If the service is HTTP, we return 80. Otherwise, we return null opt, the empty state. Think of optional as a box that might contain a value or might be empty. The caller must check before accessing the contents. You can use hasValue, the Boolean conversion, or value, or with a default. Optional is the right choice when not found or not available is a normal expected outcome, and you don't need to explain why.
Here's how optional works in practice.
Lookupenv takes a key and returns an optional string view. If the key is mode, we return release, otherwise null opt. At the call site, we use value or to provide a default. Auto mode equals lookupenv of mode, dot value or of debug. If the key exists, we get the stored value. If not, we get the default. This pattern replaces the old approach of returning a special sentinel value like -1 or an empty string. Optional makes the nothing there case explicit in the type system. Callers can't accidentally ignore it. Variant holds one of several types at a time. Here we define a token as a variant of int and string. It can be a number or a word. Both are valid token types. To work with the value, we use std_visit with a lambda. The visit calls the lambda with whatever type is currently stored. This is useful when the result isn't success or failure. It's one of multiple valid shapes. A Lexa token can be a number, a string, an operator, or a keyword. A configuration value can be an int, a bool, or a string. Variant models these alternatives without inheritance or heap allocation. Expected is the most powerful of the 3. It holds either a value on success or a typed error on failure. We define a pass error enum with 3 cases: empty input, invalid digit, and overflow. The function passInt returns expected of int, pass error. If the input is empty, we return std unexpected with the specific error. Otherwise, we return the parsed value. At the call site, expected converts to true on success and false on failure. We dereference with star to get the value or call .error to get the error type. Both paths are explicit. The caller can't accidentally ignore the error. Expected shines when errors need to propagate through layers. In load port, we first call pass int. If it fails, we forward the error immediately with std unexpected of parsed.error. If it succeeds, we validate the range. Ports must be between 1 and 65,535. If the value is out of range, we return a new error, overflow. Otherwise, we return the parsed value. The benefit: both success and error paths remain visible in normal code flow. There's no hidden control flow, no try-catch blocks interrupting the logic. Each function checks the result, handles or forwards the error, and the caller sees exactly what happened. When should you use exceptions versus expected? Use exceptions when the failure is genuinely exceptional, something that shouldn't happen in normal operation. Constructor failures, invariant violations, out-of-memory conditions. Exceptions are designed to cross many layers without each layer handling them explicitly. Use expected when local control flow should branch on success or error as a normal part of the API. Parsing, lookups, validation. These operations fail routinely, and the caller should handle the failure directly. The critical rule: don't mix both approaches casually in the same layer. Pick one model per API boundary and be consistent. 3 practices for clean error handling. First, mark important results with the nodiscard attribute. If a function returns an optional or expected, the caller should never silently ignore it. Nodiscard makes the compiler warn if the return value is unused. Second, keep error types small and domain-specific. A pass error enum with 3 cases is better than a generic error string. Typed errors enable pattern matching and compile time exhaustiveness checking. Third, preserve context at boundaries. When errors cross layers, file I/O to parsing to business logic, each layer should translate the error into its own domain vocabulary. A quick reference for choosing the right error model. Absence is normal, and no explanation is needed. Use optional. The function either finds the value or it doesn't. Multiple valid alternatives. Use variant. The result is one of several types, all of which are correct domain states. Success or typed error. Use expected. The caller needs to know specifically what went wrong. Exceptional, cross-layer failure. Use exceptions. The error should propagate up the call stack without every layer handling it. Legacy interop. Use error codes. When interfacing with C libraries or system calls that already use error codes. Match the model to the domain, and your error handling becomes documentation. 3 exercises to solidify these concepts. First, take a function that returns -1 on failure and rewrite it as returning optional of int. Replace the sentinel value with null opt. Second, take a parser that throws an exception for invalid input and rewrite it as returning expected of t, error. Make the error path explicit in the return type. Third, model a Lexa token as a variant of number, string, and operator types. Use std visit to process each alternative. These exercises force you to think about which error model fits each situation. That's the real skill.
Here's the key takeaway.
Optional for absence, variant for alternatives, expected for typed errors. Choose the model that matches the domain, and your APIs will be clearer, safer, and easier to test. For next topics, continue with advanced ranges and views to learn how to compose lazy operations on sequences using the ranges library. Then, concurrency basics for threads, mutexes, and async in modern C++. You now have the complete modern error handling toolkit. No more -1 return codes, no more exceptions for routine failures. Use the type system to make errors visible. Thank you.